But for now, let's focus on POS, intro and future, and anything else that Dr. Max has to talk about. I'm hoping he is mic'd up. His presentation's ready to go. Please welcome Dr. Max.
Okay, good morning. So we have a lot to cover. I have 130 slides, but don't let this scare you. It's going to go fast, and I hope it's going to be interesting to you. So let's get started. So what's the problem we're trying to solve, right? It's a common problem. It's trying to build applications, package them, and run them. That's a basic problem, right? It's almost like the basic problem of computer science. Well, the reality is that we've been trying to solve this problem forever, from the beginning of computer science. If you think of 1940s, 1950s, I don't know if any of you remember this, maybe a little bit. Well, what you did is you build your applications by building the software into the hardware. Alan Turing basically took tubes and plugged them and built the software that helped us defeat the Nazis in World War II. So the whole program, the packaging of it, distribution of it, was the entire stack, right? That picture on the bottom. 10 years later, IBM created the 360, right? The mainframe. So if you've watched the movie Hidden Figures, you'll see that around the time when we were trying to go to the moon, there were human calculators. They got replaced by these machines. So what's the problem we tried to solve at the time? Well, build applications, but this time you use paper, right? Punch cards. I don't remember them, but I know maybe a few of you do. And what you did is you packaged that entire application as a book. So you shipped, maybe FedEx at the time, your entire program as a book, and then somebody took it and fed it to the computer and then ran it. So that was the 1960s. 10 years later, right, 1970s, we invented something called floppies. So now you could move your app into sort of this code on tape, right? So the disk package your app. You build your app, probably with some kind of maybe punch card still. Probably at the time, people started using microcomputers. So you could use a keyboard and type your program, but you saved it on disk. And then you send those disks, right? So I do remember not quite these disks, but the evolution that came after this. So after the 1970s and 1980s, this big revolution happened because now everybody could have their own computer. So this is my era in terms of like growing up very young and having my first IBM PC. And probably most of you should remember this too. So what happened then is that you package your code into this beautiful invention called hard drive, right? You build your code, you put it in some kind of hard drive, and then eventually you distribute it and you use something called a CD-ROM, right? Any of you remember AOL sending all these CD-ROMs to everybody? Well, that was the big revolution at the time. So you package it then and then you distribute it. People take those CD-ROMs, fed them, and then ran their program. So 10 years after that, you get a little bit of a graphical revolution with Apple and certainly Microsoft changing the way we build software because now you had IDEs. And that was a big revolution. So you still use hard drives, you put your bits there, but you evolved into using some kind of an IDE that allowed you to sort of build your code, run it, and test it right there on your PC. So a big revolution, right? That's the 1990s. So most of you here should remember this. Definitely you probably were in computing. So 10 years after that, the web, right? So the web came, and all of a sudden, you could use your PC to connect to some remote server. So you package your software using IDEs, you build it, and then you shipped it to FTP on the web, right? Now that's the 2000s. We're in the 2010s. So this is the current decade, and it's the cloud, right? So what you do there is essentially, again, same problem. We're trying to build software, and we use an IDE. But this time, your entire operating system for running that app is on the cloud. At least that's what we're trying to get to. And something like Cloud Foundry, for instance, allows you to do CF push your app, and then something else runs it for you. Of course, one of the other big things that happen is web services. So microservices, for instance, having your app be divided into small pieces. Jason McGee will talk about that, internally microservices after. But you manage your apps onto this cloud, and you run them on containers. So that's kind of a brief 5 minutes over history, which you can see covers everything. Now, what's going to happen in the 2020s, we'll talk about that later. So let's revisit that initial problem, right? So it's not just about running your application on the cloud. It's also doing it in a way that is beneficial to you. So for instance, self-healing and then scalable. Because if you're just running it on the cloud, then you could just push it on a server like you did 10 years prior, right? Now with the cloud, you have a complete environment where it will run your app, it will keep it running for you, and it will also allow you to scale it up and scale it down. And that's one of the big advantages. So let's now think about this problem and see how it's being solved, right? So we claim that you do this by building your application as cloud native apps and running them on something we call a platform as a service. So what is a PaaS? And then also, what's this cloud native app business, right? So let's look at those two concepts and let's dig down. So first thing I would say is definition one is that a PaaS for me, and I think some of you might agree and other people do too, is a cloud operating system. So everybody here has a cell phone, usually an Apple cell phone or an Android, and it's all running an operating system. Well, what's on the cloud is also an operating system. And we're going to dig down into what that means and show the different pieces of it. Okay? Another piece of the definition that we need to look at is what is this thing called a cloud native application? How did it come about? What are the details of it? So we'll look at two of those two definitions one at a time, and then we'll look at concrete implementation of those definitions. So you can see the structure of the talk, right? I bring you back from Alan Turing to today, and I claim that the problem we're solving is the same problem. It evolved a little bit because you want it to be self-healing. And I will tell you how you can look at the past by solving operating system, that we've done over the past 40 years, and how you can do this today on a cloud. I'll tell you how those applications that you run on those clouds are done, and then we'll look at the future. So you're with me, hopefully. So next piece is let's take a look at what operating systems are. So this is where it gets a little bit more interesting because then operating system has concepts that we can look into in detail. And when we can see how those map into a cloud. So operating system concept, there are some basic stuff. So first thing is the firmware, right? When you have an operating system, you have to load it into some kind of a hardware system, right? Whether it be virtualized or not, it's just a hardware. It represents an abstraction that is implemented by the hardware. So you want to interface the hardware, load, and set up some I/O peripherals. That's typically what the Bootstrap does. So on a cloud OS, you will do the same thing too, except this time your hardware is what we call infrastructure as a service, and your software is a set of release packages that you're doing for your, the apps that you want to run, and you're setting up I/O that is typically network attached. Okay, so same thing, but a little bit variations on it. Another important concept in a operating system, like for instance the Linux kernel, is the core component that sort of manages execution of processes and so on, right? So in a classic operating system, all the processes are managed by the kernel, right? Another thing it tries to do is to isolate. Obviously, if you're going to run a bunch of applications or processes in one piece of hardware, you want to separate them so that they don't interfere with each other. And you provide primitives, right, so that they can communicate and so on. So that's kind of like a classic OS. On a cloud OS, you want to keep very similar things, right? You're going to manage bookkeeping, you're going to manage users, organization. So it's a little bit higher level concept, but you can see that the analogy actually works pretty well. And you want to also isolate those users and organizations from each other. So if you're running on our cloud, for instance, we can guarantee you that your applications are not going to interfere with your competitor's application that's running also on our cloud, potentially. Another important piece that the kernel does is scheduling. So now you have tons of applications, they're all coming. How do you schedule them? So this is a classic problem. You do computer science almost 101, or if you go deep into computer science, you see that this is a very important problem. How do you schedule? And how do you deal with things like, for instance, prioritization, fairness, and preemption? So you have a bunch of applications running, and one is taking a lot of the CPU, you want to preempt it. So that's a classic problem that you tend to solve in operating system. But on a cloud, it's very similar, because you're running things on a set of containers, and guess what? Those containers are taking resources. They're all consuming resources. So sometimes your scheduler has to decide when to stop and when to move a container to some other piece of the network so that it doesn't take so much CPU. So guaranteeing fairness and so on is very important. My colleague Nima works on Cloud Foundry and Diego, and I can tell you a big part of the Diego subsystem is essentially scheduling execution of these processes. So important part of Cloud OS, very similar to classic operating system. Another piece of it is I/O. So obviously, if you're running your Mac or your Intel-based PC, you want to attach things to it. Typically now we attach things wirelessly, but it's still an attachment, so it's an I/O device. Well, something has to set up that I/O connection, right? So in a classic OS, you're doing all these I/O you're setting them up in the kernel. You're allowing connections between your application and those I/O. So that's kind of a classic operating system. In a cloud OS, you're doing this, but for remote services. So in the case of, for instance, Bluemix, we provide a huge list of services that you can attach to. So managing those bindings, allowing you to connect to this remote service so that you can enhance your application with it. That's sort of the analogy. It doesn't work 100%, but you can see that there's clearly a similar thing that you're trying to do in a cloud OS. Another part that operating systems have dealt with in the past is user interface. So how do you interface it as a human being to this operating system so you can ask it to do what you want, right? So a very important piece. And for a classic OS, it's typically, and certainly in the Unix world, it's a shell where you can issue commands and you can see results. And you can essentially have a conversation with the operating system. Well, guess what? In a cloud OS, you have a similar thing too. So most of these cloud operating systems provide you with a CLI, command line interface, that you can use to do what you want. So at the beginning, I mentioned CF push. Well, that's issuing a command in Cloud Foundry to say, I want to push my app to the cloud, right? So that's the interface. Another important part of operating system evolution has been to try to make that interface easier. And obviously, Apple has done a tremendous job there to make the interface easier, and certainly Microsoft as well. And guess what? In a cloud OS, there's a similar thing too. So in classic OS, you did this because you wanted to have better productivity, make it easier, make it more accessible to everybody. In a cloud OS, you do the same thing too, except you do a web. So if you use our cloud, called Bluemix, you'll see that we have an extensive UI to allow you to do exactly this. So again, you can see that there's a very clear analogy between the classic operating system and a cloud operating system. Another important part that people don't think too much about is that when you run an application on an operating system in general, you have to package your bits. So you package your app in a certain format so that the operating system can actually run it. And this is an example of the packaging, I think, in DOS, an old operating system. but every operating system has this. So it helps you reuse, for instance, so that you're, like in the Windows world, there's the concept of DLL, which is essentially libraries that you can load dynamically. In a cloud OS, same thing too, right? Like in the OS, or at least that Docker is building, they have images. So you package your app in an image. You define an image file, right, for that. In Cloud Foundry, we have a similar thing too, called a droplet, that essentially packages your application. Another important part is the libraries, so that you can reuse existing code so you can increase your productivity. So in Classic OS, it helps you with reuse, it helps you with standardization, makes it a little bit easier. In a Cloud OS, it's exactly the same thing too, almost one-to-one, right? So you can reuse, for instance, the Ruby environment, so you don't have to package that, the cloud will package it for you. So you provide your Ruby app, the cloud does the rest. You provide your Go app, the cloud does the rest. So again, you can see I didn't force any of this. It's actually just the same problem with some different variations. So what do we want? What's the goal of an OS? Right? For a classic operating system, the goal is obviously some of the important goals are compatibility, right? So you want to be able to run your app multiple places. Execution isolation, because you don't want one app to be interfering with the other app. Easy to restart, so that your app crashes, you can just click, double click, your app restarts again. And typically it's specific to hardware, right? So like for instance, the Mac operating system only runs on the Mac, right? And it makes sense because Apple tried to maximize their hardware with their software. And this is where maybe, for CloudOS, it's different. So CloudOS, you have slightly different desideratas because you're not running for yourself, you're running for your entire organization. So one of the important pieces of a CloudOS is that it needs to provide scalability. So you don't want to have to go and manually scale your app. Ideally, it should scale by itself. So you push your app, and then the operating system manages scalability up and down for you, right? So that's one of the goals, or at least a desiderata. Another part is the isolation. You still want this, and at this point, you're not looking at isolation between just apps, you're looking at isolation potentially between organizations. So as you push your app for your organization, you want to make sure that that is separated from other apps running in other organizations, right? That's obvious, security and so on. The healing piece is an interesting piece because when you push your app on the cloud and you have thousands of users using it, it will crash. I mean, we're humans, we don't build stuff perfectly, so we write code and it crashes. So what you would like is not to have to go and double click and restart your app. You want the system to deal with that for you and self-heal. So a big part of most of these cloud operating systems is dealing with this issue, to keep the application up and running all the time. So that is an important piece. You want it to be agnostic because, 10 years ago or maybe 20 years ago, the language du jour was Java, right? Everybody here was probably like Java heads. I was one of those. Today, I literally never touch Java. I program almost exclusively in Go. It's a programming language that Google created. Why? Because it's really good. It has some very important features for the cloud. But that's today. If you talk to me 7 years ago, I know talking to Jason, I was like a big Ruby person. Now I literally only program Ruby when I have to. So the point is that this fashion that is operating, programming languages varies, right? Sort of like fashion in real life. So you want to build something to last, like a cloud operating system, and you want it to deal with the different fashion of the day. And one of the cool things is you'll see that we can achieve that. And you want it to be cloud agnostic. And this is a very important piece because you're going to build this entire operating system and you got to be able to run it on different, IaaS. So I listed a few of them, but one that I didn't list here I mean, obviously there's, GCP, which is Google's platform, SoftLayer is IBM's platform, Azure, and of course Amazon. But there's also a bunch of other ones, right? So you want that operating system for the cloud to be able to work with different virtualization of hardware, which is what the IaaS does for you. Another important piece is the notion of high availability and disaster recovery. I have a colleague that will be talking about this a little bit more detail in depth, but you can imagine that when you run something that is critical to your organization, when there's a disaster, you got to be able to recover. And ideally, there'll be no disaster, or at least you can be highly available. So you have multiple redundancy of your application. So you don't want to have to deal with this, right? This is the kind of problems where, tons of people spent years of their lives trying to solve them, either in school or in organizations, and they have very good solutions. So you want to be able to have a cloud operating system that can deal with this for you. So that's very important. So the next question that I mentioned is, is cloud native apps. So what makes a cloud native app, right? And why do we want to have cloud native app? The point here is that we provided a series of goals and desiderata that we wanted out of your cloud operating system. So to achieve that, one way is to say, well, there are some applications that you can run that will allow this to happen, and some probably not, or you'll have to work a little bit harder. So one of the things that happened over the past 5 years is that people sort of, as we started running stuff in the cloud, is realize that there are sort of these 12 characteristics that if you try to build your apps with those characteristics, they can generally achieve those goals that we mentioned. And that's what we call the 12-factor, or 12 factors, right? So when you have your cloud application follow these, then they quote-unquote cloud native, and therefore sort of follow the 12 factors. Now again, this is a little bit of dogma, so don't look at it as this is the truth. It's more a pattern. It's more of, I guess, what we as an industry realize is good. So don't look at it as you have to do this, and if you don't, then it's not 12-factor, and oh my God, the world is gonna, fall apart. Not the case, but you try to follow these. So let's look at each one of them one by one very quickly. So one of the first things you want to do is you put your stuff on, version control. And obviously, everybody here has GitHub. You put it on GitHub. As a matter of fact, if you don't have a GitHub account, one thing you could get out of this talk is you get a GitHub account, and I've done my job. But hopefully, that's not the case for anybody here. You try to isolate your dependencies. So separate your dependencies from your actual application. So don't bake it in, right? Separate it. That's one of the important things. Configuration, for instance, is another piece that you want to have as a separate thing, like in a file, for instance, or ideally better in a database, in JSON database, for instance. You can do that. Services are essentially remote resources. So for instance, something like a database, you treat them as that. A very important piece is separate your build and your run. So typically you have some kind of a continuous integration that helps you achieve that. So again, most of you should be very familiar with this. If you're not, that's the kind of things you can pick up very quickly. This one is probably one of the more important ones, where you try to have your app be stateless. So if you have any state, the state should be in a database. The reason for this is because your app will crash. And if you keep your state in your app, that state dies when your app dies. So the system, the cloud operating system, will try to restart your app, but that state is not going to be able to be recreated. But if your state is in a database, then you can load it. So that's very important. Port binding, so this is the case where your app runs, crashes. It needs to be able to reattach to your ports. So essentially the external resources. This is probably the other very important one. So the order is just in the order that the 12-factor people posted, but I think this is probably one of the most important ones. Because what it says to you is, don't try to scale your app by just trying to push it into a bigger container or a bigger VM. Instead, try to replicate it. So scale your app horizontally versus vertically. Okay? So that's a very important kind of like truth that we've discovered over the years. Ideally, because things fail, you should design for failure. What I mean by this is you don't design to make it fail, but you design that when it fails, it can recover. So one example of this is since your state is from the database, when it restarts, it goes, fetches the data from the database, and shows to the user pretty much, hopefully, close to where they were the last time they used your app. So you design for failing gracefully. This is one where people don't realize this until you hit this problem. But another important thing to remember is this is so true. What that says to you is when you build your app, especially when you're going for scale, meaning thousands of users to hundreds of thousands of users, one of the things that tends to happen is that your test environment or your development environment and your production environment are different. And the reason, it's obvious, right? So your production environment is going to be designed for 100,000 of users. Well, you're going to have to like probably deploy it like 100 times, 100 versions of your app, right? And then bigger database and so on. The problem with that approach is that problems that occur, like code problem, bugs that exist in your software in production will only show in production. Because like, for instance, a simple example of this is a query. You make a query to the database. Well, obviously, if your data set is big, your query might, if your query is not optimized, it might take more time. So having your production, your development, and your test environment be close to each other. It doesn't have to be exactly the same, but it has to be close enough that you can deal with it. I know, for instance, that there's a researcher. Before joining IBM Clouds, I was in IBM Research. And Twitter, if you remember, which is famous now, I guess somebody somewhere in Washington uses it a lot. But anyways, Twitter used to crash all the time. It doesn't crash anymore. And one of the big problems was they were not doing this based on what came out of a lot of work that they've done to improve it. So this is very important. If you take another thing here, because it's not obvious that you need to do this. So your test environment data should be close to where you want your application to run in production. Another piece is having all your logs be streamed. This is obvious to the point where things will fail. You need to be able to discover what happened. Having one stream allows you to see the times of when things fail and then try to debug. And then finally, administration tasks should not be things where you stop the system and run them. They should be one-off processes. So you got to be able to run app administration tasks all the time. So updating your database, improving things, and so on. So these are the 12 factors, right? So what are your options for cloud operating system? So we've mentioned, kind of the history. We looked at operating system. We claimed that operating system in the cloud should provide all of these. And we even said there are more things we want, like scalability, self-healing, and so on. So what are the options that exist today? So let's review that. And I will make the case for one option that we, IBM, are backing. I hope you realize that it's actually the right option. So first thing to kind of look at the space is to say, well, one dimension is to say, well, what's open and what's private, right? And if you probably also believe in open source. So obviously open is on the top because we want things to be more open. It doesn't have to be always open, but the more open, if it's good, that's usually better. So better goes up, right? And we did a lot of things private. So I'm not trying to say we don't want to do it private. We do tons of things private. So that happens too. The other thing is, I claim, and some people might disagree with this a little bit, is that you want to move closer to PaaS than IaaS. And the reason for this, again, is if it was just IaaS, then I would just give you all your Mac with no operating system, and then you have to build everything. Well, clearly, that's not the solution, right? You want to have software that helps you. That's the whole reason. And then eventually, you want to have AI that helps you, right? So I think positivity goes from left to right, your left to your right. So the first choice could be AWS. I mean, they do a fantastic job. They provide pretty much a lot of pieces that would allow you to build application that meet the desiderata that I mentioned, right? But it's private. Let's just be honest, right? They do a fantastic job, as I said, but it's private, and it's mostly geared towards IaaS, because that's where they started. So I don't think AWS is the right choice to deal with the problems we mentioned. The next part is Azure. So Microsoft has improved Azure to a point where now it provides a lot of the features that we mentioned. It's absolutely fantastic. It does a decent job, and so on. But it is, again, private, right, mostly. And it's sort of in between the IaaS and the PaaS because it provides IaaS and provides PaaS, and it's sort of in that space. Another one is Docker, right? It's kind of super hot these days, and they provide more and more features. It's definitely open, so it's open source. You can look at the code, and you can make changes. You can fork it, and so on. But I believe that it's mostly in the IaaS. It's gradually migrating towards PaaS, but it's mostly in the IaaS section, mainly because you're dealing with containers, and you're just pushing stuff, and so on. Again, nothing wrong with that, because if your application deals with this, that's fine. But if you want to provide a experience like what I mentioned to you, like an operating system, sort of the same experience that you have on your iPhone, that you don't have to deal with details, you just download apps, run them, and then the system deals with them for you. I think you want to be more on the right side of the world. Heroku is a very good example of one that provides exactly that, right? So they are very much a PaaS, but they are private. So they got bought by Salesforce.com a while ago, and they kept them private. And if that's okay with you, then that's fine, right? You can stay there. A very important one that's coming along these days is Kubernetes. So it provides a really nice container services management. And if you add on top of this something like OpenShift, and increasingly even us, we are supporting Kubernetes, then you have a decent solution for this. So there's no complaint there. So it's both a PaaS and also open. But I believe the one that sort of fits the sweet spot is Cloud Foundry, because it's both open and it's both a PaaS, and it provides all of those features. So that's my claim, and this is part of why we have it one of our key pillars to our IBM Cloud solution. So it's all open. So what is CF and what are the concepts? So let's go over them very quickly, and we'll try to map the concept that exists in CF to what we mentioned before. I'll have to go a little bit fast because we've got to go to the next stages. But there is this thing called BOSH in CF. Well, guess what it does? It's the firmware. It allows you to load the entire operating system into your hardware. And guess what? It supports all of these clouds that I mentioned. All of them, and more. You can even take CF and run it on Kubernetes. You can take CF and run it on Photon OS. So that magic, quote unquote, is provided by BOSH. And it does it in a self-healing fashion, because your different components in CF, if they go down, the BOSH director will deal with it. I know a lot about BOSH because I essentially spend a lot of time working with them. I work essentially programming with the BOSH team. So that's BOSH. Another piece is CAPI, which is sort of the Cloud Controller API. And that, I think, as the kernel API. So it provides all the feature that you talk to when you're trying to deal with Cloud Foundry kernel. Okay? So it's kind of complicated, but think of it as a huge API with a database and concepts like organization, users, and dealing with access control and so on, right? So it's kind of a complex system, but it exists for that. Another piece that got re-engineered in the past couple years is called Diego. And it's essentially the scheduler, and it provides a little bit more because it also helps with the isolation a little bit, and it does, dealing with also, self-healing. But the Diego subsystem essentially allows you to run long-running processes as well as short-running processes. So it allows you to schedule those things and run them and manage them in an efficient manner, right? So it's the kernel piece of the scheduler, or the scheduling piece of the kernel. Another important piece is called Garden, and increasingly Garden runs C because it's based on a standard. It provides this app isolation. So it's essentially the container piece. So when you look at Docker and you see all the different pieces that Docker has, it started with a container management system, and Garden is an equivalent of that. And it's based on Run C, which makes it sort of compatible with these other Run C compatible container management systems. So what that does is provide a kernel piece that provides isolation to your application. So when you run an application on Cloud Foundry, it's running on a Garden container, and Garden will guarantee for you a level of isolation from the rest of the other containers and allows you to move them and so on. My colleague, Jules Friedman, might be here, or he'll be here this week. He essentially is the PM for that project, so you want to understand the details behind it, talk to him. So he's a good guy to talk to. Another part of Cloud Foundry that sort of maps to what we discussed before is the build pack. So what is that? Is essentially how you package all of this software that you want to run on Cloud Foundry, right? Because you don't want to have to repackage it manually. You want the system to do it for you, and what it does is it uses those build packs. So when you say your application is a Go application, it will get all the necessary Go subsystem for you into your package app so it can run it. And it does this now on what we call a Diego, actually it's a Diego cell. That's one of the changes to my slides, but I'll fix that. CF services, a very important part of Cloud Foundry, because what that does is it allows you to extend the platform. And this is where, for instance, a lot of our AI services will come in. So it's a complex subsystem that actually is becoming a standard in itself. So if you're interested in this, you can look into Open Service API. And as a matter of fact, the Kubernetes community is adopting this as part of how you can extend Kubernetes with services. So CF services is that. I know a lot of it because I worked on it as well. And if you're interested, we can talk offline on how that works and if you want to create your own services and so on. The CF CLI provides you with a nice interface to the platform. So you can push your apps, delete your app, clone your app, scale them. I mean, you name it, you can do create users, delete users, organization, You do all of this with the user interface. And obviously, as I mentioned to you, something like Bluemix provides a graphical user interface on top of this to make it easier. Logaggregator allows you to see all the logs. So this is a subsystem in the cloud operating system called Cloud Foundry that allows you to aggregate all of your logs. And if you want to get those logs into your proprietary database, you can do that because you can provide your own hook into it. UAA is a component called User Authentication and Management or Account Management that allows you to essentially deal with your users. And what's great about UAA is that you can connect it to your own directory service. So if you have existing directory service, you can plug that UAA into your directory service so you don't have to recreate those users, recreate those organizations, and so on. So you can make them work together. But there's more. So one of the things that I've been doing in Cloud Foundry is to extend it, to provide sort of extensions to Cloud Foundry. So one component is called Abacus, this led by IBM, where we essentially added the ability for you to meter the usage of Cloud Foundry. So obviously, if you're a cloud operator, you want to be able to know how people are using it so you can charge them. So that's how we do this in Bluemix. And we do this with this pipeline called Abacus, which is open source. Another piece is persistent storage. Sometimes this 12-factor stuff is not too good, or at least you have applications that don't follow it, and you still want to run them on a cloud. Or maybe your application uses a stream of data that it has to operate on. A lot of AI applications do this. And if you have that case, you want to have a storage that is persistent, so that if your app crashes, the subsystem will reattach that storage to your app. And this is something we did with EMC to provide that. So Cloud Foundry provides that. Networking, this is a pretty basic one, where basic in terms of the concept, more difficult to implement. But the idea is that as you build microservices, so you divide your app into small pieces, well, you want those things to talk to each other very fast and also in a very secure fashion. You don't want it to have to go to the internet and back. So you can set up networks that are private to these components. So you can do exactly that now in Cloud Foundry. API description, this is the part where as the platform evolves, we are exposing APIs where we want to describe them into the open API description language, which is based on Swagger. So we're increasingly doing that as well. Isolation group, this is another piece that we've also provided, which essentially allows you to guarantee that not only your app will be separated because of the software, so Garden will help you do that. So when you run your app in different containers, those containers can't talk to each other. But there's a potential that there is a virus or something like this, or people are very paranoid and they want to guarantee that my app is running on a completely different hardware than the other person's app, or separated. You can do this now with isolation segments. So you can say, I want these apps to be on this piece of hardware and these other apps to be over there. So you can do that now. Auto scaling, this is a component IBM is leading, where we are essentially saying, yes, you can scale, but we will do better than just allowing you to scale by saying, hey, multiply my app. We will monitor the system, and as some triggers happen, so for instance, the amount of requests to your app is increasing, we will scale up automatically. And then obviously, we can also provide ways for you to scale down. So you can do all of this through a service. So what is Bluemix? Bluemix, first definition, is our productization of Cloud Foundry, right? So it provides dashboard, very extensive catalog, and I'll show you a few pictures of this, and a few more things. And this is where I want to be clear that Bluemix actually provides a lot more than this, because Bluemix also provides containers. And recently, there is essentially containers based on Kubernetes. So when you go to Bluemix, you not only get an operating system that deals with your apps, you get an operating system that also allows you to deal with containers. So if you want to deal with containers directly, be our guest, you can do that. It provides even virtual machines. So if you want to run on a, say for instance, a bare metal machine because you want to have a dedicated piece of hardware running your app, you can do that. It provides this thing called functions. So increasingly, especially for AI, people are using functions to divide their application. So this means serverless computing. And there is this thing called OpenWhisk, which is also open source, that is part of Bluemix. So now you can build your apps using that. So what's going to happen in the 2020s? Nobody knows. I don't have a crystal ball. But we can kind of imagine, use our intellectual ability to say, hey, maybe in the 2020s, the new stuff, as you remember at the beginning, I mentioned those decades. And we get to 2010s, which is where we are now. The problem is 2010s is sort of ending because we're almost at the end of 2017. So we have 2 more years where it's going to start getting into 2020. So in 2020, will it be the AI revolution? I think it probably will be. I'm not 100% sure, but I think there's a good chance that it's going to be. So what's going to happen if that happens, if it becomes the AI revolution, right? I don't think writing code is going to change. I don't think you're going to build an AI that's going to just like write the code for you. If you do that, great. I'll come work for you. Or maybe we can figure out a way to merge, and so on. But the point is that writing, having an AI that writes code for you, I don't think that's going to happen. But definitely what's going to happen is allowing an AI to deal with the vast amount of data that we're collecting. So enhancing your application. So I think that's an obvious one. IoT devices, so in other words, instead of having all of your apps be just cell phones or laptops, having them like you see now in a bunch of devices, I think that's going to be a key. And then increasing the management of your application in the cloud to a point where even your auto scaling and all of this can be completely done for you by the AI. So will you trust your AI to do this for you? I think increasingly that's going to be the future. So how does our solution, this is maybe where it becomes more of a sales pitch, if you may, is how does IBM, for instance, deals with that coming revolution? Well, one of the things we've done is IBM Watson, right? So IBM Watson is this sort of big AI that came from years and years of IBM research to, at first, beat a human in Jeopardy. The problem, though, is that by beating a human in jeopardy, you had to solve a series of problems that actually happens to be common problem that people need to solve in various industries. So with Watson, you sort of have a set of services that you can expose. So if you remember, I mentioned to you that what you have in Cloud Foundry, and specifically in Bluemix or all Cloud Foundry, is the ability for you to have a huge catalog of services. So one of the things that we did at IBM is to expose all of these services that Watson provided as separate granular services, so you can use them. So example of these things are things like speech to text, text to speech, ranking of data sets, taking a huge amount of unstructured data and providing structure around it, visual recognition. There's a very cool example there where you can take a picture of anybody and then plug it in, and it will recognize it and give you a huge amount of attributes to that. A very good example that I like to do is I like to take a picture of Kanye West and drop it in there, and you could take any picture of him, and it turns out it will be very, very good at identifying this person as a rapper, as being famous, and chances are it's Kanye West. And that's all through the AI. But that's just an example. So what we've done with IBM Watson is to sort of split the different pieces of it and expose them to services, and those services you can integrate into your applications right now. So you can get ready for this coming revolution. So these are examples of all of the different pieces, and there's more coming. So things like text analysis, data analysis, IoT, translation, and NLP. You can do tone analysis, you can do sentiment analysis, so you can provide huge amount of text and find out if the text is being positive, if it's being negative, and so on. All of this happens through these services. So that's Bluemix. And I believe it's not only a PaaS that's built for today, but it's also built for tomorrow. And it's built on open source. So with that, I will see if you have any questions. Thank you. So here are some references.